Hello everyone, my name is Zhiqi and I'm a second-year PhD student from INRIA, France. I'm presenting today our work, a soft nearest neighbor framework for continual semi-supervised learning. Continual learning deals with a dynamic learning scenario where the model learns from a sequence of tasks. We're specifically interested in a semi-supervised setting. Why is it realistic and interesting? If we consider a fully supervised learning scenario where we annotate the entire dataset, the labeling operation can be expensive or even impractical for some online applications. Instead, a self-supervised setting where we do not annotate any data results in an expensive and complex training procedure. We believe that semi-supervised setting finds a good trade-off between them, as the limited annotation can still provide strong learning signal. As you can see, for each task, we have now both labeled and unlabeled data. With the new scenario comes the new challenges. We found that the model will not only suffer from forgetting, as in standard continual learning, but also risk to overfit the small label set when learning the new tasks. You might ask, okay, but what if we just use conventional methods like either continual learning or semi-supervised learning? What will happen? Here in this figure, the x-axis shows the percentage of label data in a continuous semi-supervised setting, and the y-axis shows the average accuracy of the method. The blue curve is the performance of our method as a reference. The pink curve shows that continual learning methods perform poorly with very few label data. Then a standard semi-supervised method can have good performance with very small label sets, but it is upper bounded by its poor continual learning capacity. In the end, we also found that existing continual semi-supervised methods only show limited improvement. A conclusion here is that we definitely need a more powerful method. So we propose NNCSL, which is specifically designed to solve the two issues we mentioned above. We start with the overfitting problem. The starting point of our method is PASS, a standard semi-supervised learning method based on nearest neighbor techniques. It caught our attention because it does not use label data directly as training samples, which largely reduce the overfitting problem to the label set. However, PASS is not designed for continual learning. First, PASS assumes the same distribution of labeled and unlabeled data. It is not the case for continual learning because we have a shifting data distribution. So we propose to use a filter to keep only data for current tasks. Another drawback is that PASS is designed as a two-stage method with pre-training and fine-tuning, but it is not clear which one should be used for following tasks in continual learning. Instead, we propose to directly attach a linear classifier, which merges two-stage method into one and also provides stronger learning signal to stabilize the training. With all these modifications, we have our base learner CSL. After that, we propose a novel module to retain knowledge and fight against forgetting. Since our framework uses nearest neighbor to assign procedural labels, we believe that the non-linearity of the nearest neighbor can be beneficial for transferring the knowledge. Thus, we introduce a novel distillation loss nearest neighbor distillation, NND, which has the following advantages versus standard knowledge distillation, KD. First, it captures and transfers nonlinear relationships of classes, unlike KD, which is linear. Second, it distills sample-wise relationships, unlike KD, which is a class level. Third, it introduces a randomness to regularize the model. And in the end, it balances well between local and global information. We performed experiments on CIFAR 10, CIFAR 100, and we were the first one to introduce a larger scale and higher resolution datasets, ImageNet 100, in continual semi-supervised learning. We use average accuracy as an evaluation matrix and allows for a memory buffer of different size. We compared with various related works which fit in this setting. Here's again the figure of label data percentage versus average accuracy. One remark here is that our method with only 0.8% of label data can surpass many existing work with 25%. This shows the effectiveness of our method. After that, in this figure, you're seeing the average accuracy after each task in a 10-task setting. As an ablation study, we show that CSL is better than PASS, and the additional NND can make NNCSL better than CSL. It confirms the effectiveness of each component of our proposed method. In the end, the figure follows the same spirit as the last one, but with a 20-task setting on ImageNet 100. We can see that our method outperforms existing works with a large margin. That's all. Thank you for your attention.